AM64x Linux boot process presentation. We are going to go through the AM64x from device initialization, so from before anything's going on, even in hardware, up until how do you get to a Linux kernel prompt. Here's how we plan to go through it today. We'll have a short overview of Sotara and AM64x, very short, I promise, just to make sure that everybody knows what we're talking about in case you haven't looked at this device before or it's new to you. There is some specifics about it that definitely apply to how it boots that we want to make sure that everybody's on the same page before we get going too far. Then we'll get into device initialization, so some of the hardware stuff that's got to happen. We'll just cover that briefly so you know what a good device power on reset looks like. Then we'll get into the boot architecture and the flow and how it proceeds, and then we'll go through Linux as well and talk specifically about how Linux boots. And then if everything works out well, and you know how demos go and you do them live, I will try to demo to you a AM64x starter kit booting Linux, and we can look at some of the details there and some of the files that are being used to validate what we talked about. And then we'll summarize quickly and, of course, try to keep everything on time and get you back to what I hope is a wonderful day. So once again, we do very much appreciate you joining us today. We hope this is good information for you. And like I said, keep the questions coming through the chat and through the Q&A, and we will try to address those as best we can during the presentation. All right, so let's look at Sotara, just in case you haven't been exposed to this recently. Sotara is a line of MPUs, all right, or so microprocessors. These are larger devices when compared to MCUs or microcontrollers. They typically have a Cortex-A type of ARM core, which is an applications processor type core like a Cortex-A53 that we'll be discussing today. And they've got a rich array of peripherals and connectivity, as well as this device has a variety of other processing cores that are used in it that enable you to do a variety of different things. So we'll see those today, and we'll see how that kind of makes the boot process a little bit more dynamic and interesting. So we'll cover all of that today as we go through it. So this is our product family that really covers Cortex-A type processors. We also have our Jacinto line of processors, which has even higher end Cortex-A processors. And between those two, those kind of serve as TI's applications processor lineup. Below that, we have a number of MCU lines as well. And across that processor range, you can usually define a device that is going to meet your needs. And we try to do the best we can to present that to you in a unified platform that you can utilize and take advantage of. For example, unified software definitely crosses the MPU portfolio. We offer Linux for all of our Cortex-A processors. And of course, Linux is one of the most popular, if not the most popular, embedded operating system out there. And that provides a great way to get started and a common infrastructure to use to start your application design. All right, so that's Sotara. Here is the device itself. This is the AM64x, which comes in another number of product numbers or SKUs. But the overall device architecture, like I said, is based on these Cortex-A53 application cores from ARM. These go up to a gigahertz in performance. They have a dedicated L2 architecture to be able to run high-level operating systems like Linux. Then we have another of other cores that we'll be talking about today because they are involved in the boot process. The most important ones are these real-time cores over here. These are up to 4 Cortex R5F cores from ARM that you can utilize with this device. We also have an MCU that is set off to itself. That's a Cortex M4. And we have some TI proprietary cores that are called the PRU ICSS, which enable you to do a number of real-time functions, including real-time industrial protocols, like some of those that are listed here. And of course, we connect that all up with DDR so that you can run things like Linux and a number of connectivity peripherals, including a 2-port gigabit Ethernet switch, a PCIe, USB 3. We have a GPMC that's good for FPGAs and certain memories like NAND and NOR, and then a wide range of other peripherals as well. And the last thing I want to mention is this security accelerator, because it comes into the boot process as well. So make sure you recognize this. This is actually a dedicated core for this function. So we'll see that come into the boot flow as well. All right. And we provide, like I said, a number of these with different numbers of Cortex A53s, different numbers of Cortex R5s, and different mixes of peripherals to be able to select whatever meets your needs best for your design. All right, so that's the device. We'll be digging into this in quite a bit of detail. So just wanted to make sure that everybody had a good overview of what this device family is. It's a modern 64-bit Cortex-A architecture, and it's got a lot of interprocessor capability to be able to do real-time communication, real-time processing, general purpose processing with the Cortex-A, is running high-level operating systems like Linux with a number of connectivity peripherals. All right. So you're going to have a number of processors. It doesn't do you any good if you don't have software, since we need software to drive all of these embedded systems these days. And we do have a code compatibility scheme with our software development kits, or our SDKs, across a wide number of platforms and applications that allow you to use your knowledge and the base SDK offering to build up a number of different things, from automotive to industrial and different applications like that. And you can see that we've got a variety of things that we serve as the foundation for that. Things like we need to have system performance for a lot of this. That's why it's an MPU line, TSN or other standard networking connections, decent level of integration and system cost, so that you can get the right price point for your application in an embedded system. Safety and security, we'll be talking a little bit about security today, or we'll be referring to it. And of course, a wide range of just tools and software partners to make all of this come together and make it accessible to you. All right, so with that, like I said, I hope that was a short overview. We're going to dive right into the boot overview on the AM64x device. All right, so here's the overall process. And of course, most of this is your hardware process. So we have your pre-initialization stage, where we're making sure that we have a valid system startup. And this is mostly done in hardware, of course. Then you have your power clock and reset ramp sequence. So this is where all the signals coming in the device are meeting the right data sheet requirements to make sure that this is a valid boot. And then the first thing that's actually going to run on the device, as far as some version of software goes, is ROM code. And you know, that this process so far is pretty standard, right? If I go back to an AM335X device that's been around for a number of years, and even I could go further than that, this is pretty much standard, right? This is how most devices start. The process after this is where things are going to get interesting, because you saw that we have a number of cores, and one of those being a security and device manager. So we're going to have a couple of different ROM codes running. And that's where this starts to diverge maybe away from a traditional system that you're used to. And we'll show you all of that. After the ROM codes run, of course, we've got our initial software, and that can be a secondary bootloader or a secondary program loader, depending on what you like to call that. And eventually, of course, what our goal is to get up to a high-level operating system, or your embedded application if you're running that on an RTOS or something like that. Okay. So hopefully I hit all these details down here in the text. I won't go through and read those again for you. And we're going to hit each one of those concepts a little bit more heavily. So I'm just going to go ahead and roll forward. I'll just highlight that we're going to do some hardware stuff that's going to get us to a valid point in the chip to start running code. The first code that's going to run is our ROM code. And then we're going to switch over to different phases of software to get us up to a high-level operating system like Linux. The pieces of the architecture that are going to come into play for the boot are highlighted in this diagram. So the security accelerator that I mentioned, we also actually call our DMSC, our device management and security controller. All right, so that's a specific core that we have on the device to handle security and other device management functions. And it is actually one of the first cores that starts running. So we'll look at it. And then we also leverage our MCU Cortex R5F cores. One of those, the primary, is going to be the primary boot device. So it's going to start running very quickly with DMSC. And we're going to use some hardware to make decisions about how to actually do the boot process. And those are our boot mode pins. So there's 16 pins on the device that we're actually going to sample at reset that are going to help determine what happens with the boot flow device. And if you've seen something like that before, it's mainly, what kind of configuration do we have? What port do we want to use for the SD card controller? Are we going to use 8-bit or 4-bit mode? Stuff like that is all going to be communicated to the device through the boot mode pins. So those are very important, obviously, for the boot mode process. And we'll be looking at those and make sure you understand those and how that contributes to the boot flow as well. All right, so I'm just going to pause there for a second, let you kind of absorb all of this. Relatively large, somewhat complex device, got a lot of capability, and the boot flow is definitely going to be a little bit more complicated than a typical MCU, certainly, for example. All right, but not really that different than any other modern applications type processors that are providing a lot of security and safety functions. All right, so here is some specifics on those. We have the different cores, so that's the first two bullets, and the different images that those cores are going to be running. All right, so cores and images. All right, so the hardware and what they're going to be running. All right, so DMSC, like I said, stands for Device Management and Security Controller. So if you've seen that term and wondered what in the world is that thing and is that new and stuff like that, yes. This is a new feature of our architecture and the 64-bit realm to provide consistent device management and security controller for things like safety and obviously for security of systems. We have a dedicated core that is kind of watching the rest of the system to make sure that everything's working right, and it can be configured in a variety of ways to make sure that the system behaves so that you don't go off and do stuff you're not supposed to help with a security attack or a safety type function. All right, so it's going to actually be the first thing that runs. It's going to run its ROM code, and then it's going to go get an image to run, and that image is called system firmware, and that's our runtime image that the DMSC is going to run. All right, so DMSC runs system firmware, and system firmware is going to provide runtime functions for a variety of functions, and we'll get into more detail here in a couple of slides that help the system be configured and operate correctly in a safe and secure manner. All right, the first general purpose core that runs is the Cortex R5, and this is our R5.0, which is on all our devices because it is a primary boot controller coming out of reset. So this is one of our R5Fs, and it's going to run its own ROM code to start out with. It's going to communicate with DMSC on how to go do certain things, and eventually it's going to run its secondary loader, which can be an SBL in an RTOS or a generic environment, or an SPL in a U-boot or Linux environment. All right. So 2 cores start running, DMSC, Cortex R5, your main boot controller, and they will each run, obviously, their own images. And then the boot mode pins are what's going to communicate to the device where to go get these next level of images. All right, so you do have some options there. It's not like you have to put them in one place. You get a variety of memory and peripheral options for actually go get this next level of boot to keep the boot process going. And I see they've got a question from someone that wanted to be able to watch this later. And yes, we do record the video, like I said, and I will post a recording of the video. It usually takes a week or two to get that up. And I post that on the original E2E ticket where you probably found how to register for the webinar. And we also put it on our webinar page. So if you have to leave or want to share this with somebody else in your team, we do provide a recording of it. And then we got another question, is DMSC something like HSM? Similar. As we go through this and you see some of the functions that DMSC is running, I think that will be more clear how DMSC and an HSM or a hardware security module, how those are similar but also a little bit different. So I think we'll clarify that as we go through the presentation. So thank you for the questions. I hope you keep them coming. Certainly think makes the not only this presentation better, But if you've ever watched one of these after the fact, it certainly is a lot more interesting to hear some question and answer and back and forth as opposed to me droning on slide after slide and putting you to sleep, which is not my goal today. Believe it or not, I'm really not trying to do that. All right, so let's go through this kind of in a step-by-step fashion, looking mainly at the ROM boot flow. All right, so how do we get up and running as a device? How do we start executing the ROM? What are some of the things the ROM does? And then how do we get to the next level of boot? That would be your system firmware for your DMSC and your SBL or SPL for your R5. How do we do that? All right, so let's go through this. So you see that I've got our cores over here on the timeline, so DMSC and R5F as we've talked about. And then we're going to show how the other cores actually get brought into the picture once these two get the system brought up and configured and ready for a secure environment. Okay? All right, so here we go. So first thing you need is a valid power on reset, right? So your power infrastructure on your board needs to provide a valid power sequencing, a valid power signal, and then a valid reset signal to say, okay, we believe you're ready to go. The device is going to validate that, and if it's a valid power on reset, the first thing it's going to do is start running the DMSC ROM code. All right, so DMSC ROM code runs first. And its first thing is to do is to, once it does some basic initialization, make sure that the R5F gets up and running. So we now have two cores running their ROM codes in parallel to get the chip ready to rock and roll. All right, so DMSC ROM runs first, resets and releases the R5 to run its ROM, and it runs its ROM to start doing the next stage of boot once it does its basic initialization. So first thing we need to do, obviously, is go find the R5F next stage bootloader. In this example, we're using SBL. All right, so this is a secondary bootloader. Could be for an RTOS application or something like this, or really whatever other code you wanted to run, as long as it meets the needs of this. And to do this, what we're going to do is we're going to make sure that you have a valid image, right? So we're not going to just go run whatever code happens to be out there, because that's not a safe system. We're going to make sure that it's a valid image. We're going to go get it from whatever memory or peripheral we've stated via the boot mode pins. All right, so that's called out here. And then once we know where to go get that, we'll go get the image. We'll figure out where it is, copy it into memory, and get ready to start running it. And then once DMSC is happy with that it's a valid image, it will allow the R5 to go off and start executing that image. Okay. So we got to our secondary bootloader on our R5F. DMSC is going to run its ROM course. And of course, we need to go get the next stage of DMSC's execution timeline, which, if you remember correctly, and if you do, you get bonus points. It's called system firmware. All right. So we need to go figure out where our system firmware is as the next stage of DMSC execution. And then we'll go load that. And this is kind of a little dance between the R5F and the DMSC. The R5F is actually going to go get the image and copy it into internal memory. DMSC is going to validate that image and say, yep, that's a good system firmware, before it copies that into internal memory to the core that it's going to run on and then starts executing that. All right, so it's a little bit of a communication between the R5F and the DMSC to make sure that we get a valid system firmware, because this system firmware is going to provide the configuration for the device to make sure that it's set up in the proper configuration for the application for which it was designed. And that, of course, gives us our system firmware. And now we're running our runtime services once we get through with the ROM. And we've got our SBL running on our R5F. And of course, now we need to get to the next stage of boot for the rest of the system, which is going to be done through the R5F in conjunction with the runtime services provided by the system firmware. All right, so there's our firmware services offerings, for example. We're going to start going off and figuring out the next images to get, how to validate those, make sure that they're either secure or safe, and then start loading those up to other cores. All right, once we know we have valid images, we have the configuration ready to go, the device is ready to start executing, then we can release other cores like the Cortex-A53s to run Linux, or the other R5Fs, or the Cortex-M4 for a safety application, depending, of course, on how this bootloader was set up and what it was designed to do. Okay, and that gets us up and running. As those cores come up and running, they're going to continue to use the runtime services provided by the system firmware through an API called our system firmware client, or SCI, to check, validate, and configure the rest of the device. For example, if a Linux driver is invoked and it needs a clock signal, it's going to ask that for that clock signal to be configured through DMSC. So now you don't have drivers that can go off and configure clocks and mess up the rest of the system, therefore making it unsafe or making it unreliable, right? So that's one small example. Now, we provide a lot of those drivers for you, so you don't necessarily have to know those details, but if you're got that curious engineering mind to know how this is working, go look at one of the drivers that we provide, and you'll see some SCI client calls that are configuring things like clocks and memory and things like this to get the system configured and up and working correctly. All right, so I'm going to pause again, just let you stare at that for a second. I realize that's a lot of information, and just remind you that all we've done at this point is getting through the SBL, and we've got system firmware up and running, and we kind of have an idea how the cores run, but we don't know what images they're running or how they got there yet. So we need to fill that information out to make your knowledge of the boot flow complete. All right. So with that, I'm going to pause for questions. I don't see any on the chat. Hong, have you seen anything that maybe I missed, or any comments you have from your side?
So far, only one question. I think you already answered for the HSM, like eMMC. So far, so good. Excellent. No more new questions.
Good, good. All right. Well, keep those questions coming. I know this is a lot of new information. And we certainly want to answer your questions and make sure you get the information you came for as well. But we'll continue to roll through the presentation since we're about halfway through already, and I've got a lot of stuff to get through. So we'll continue to go, but your questions serve as kind of a real-time feedback loop for whether I'm going too fast or too slow and stuff like that. So feel free to ask questions. All right, so let's come back to the device. We talked about these boot mode pins and how they are used throughout the early boot process to make certain decisions. Remember, these pins are on the device and they are sampled at power on reset to help make some decisions about the boot process. Namely, where are the images coming from and how are the memory or peripherals configured that are going to store those images to complete the boot process. So let's look a little bit more at these. So here is the picture from the technical reference manual of what these bits do. And so you can see that the first three do PLL configuration. You have to know what your base clock is to be able to set everything up appropriately. So that's part of that. You have your primary boot mode config, and then even secondary options as well. And we're going to look at each one of these three, which are the main ones, in a bit more detail. All right, so this is the TRM telling you what these different settings are going to do to the boot process. All right, and this is contained in chapter 4, the initialization chapter of the TRM. So if you want to go get something that will just be an amazing read, really, really fun stuff, guaranteed to keep you wide awake for hours. I'm just kidding. It's a lot of detail. It's important stuff, obviously, and if you're building a system, you do need to know it. But there's a lot of little details that you have to work through. So take it in small chunks is my recommendation. But that's in chapter 4 of the TRM. All right, so let's look at each one of these. So like I said, the PLL configuration just tells us what clock are we running at, right? So we support a variety of clocks. Our boards have different configurations. And so you can see how you want to tell the device what clock you're feeding it so that it can do that. And that's done via these lower 3 bits of the boot mode pins. Okay. All right. Now let's look at the more interesting ones. So these are your primary boot mode sources. All right. So you can see them listed here. And it's all the ones you would expect given the peripherals that we listed in the beginning. You have OSPI or 8-bit 8-bit wide SPI flash, you have quad SPI, 4-bit wide SPI flash, 1-bit mode SPI flash, Ethernet, I2C, and you can read them. I don't know to either either one, but a wide variety of boot sources for you to choose from for the primary location of where those images are going to be stored to continue the boot process for both your system firmware, your R5F, SBL, or SPL, and of course the images are going to be needed after that we'll get into in the rest of the story here. All right. So let's take a little closer look at each one of these because this is a little different than the way TI did this with our Cortex V7 products like AM325X. So in that, each one of these sequences would be kind of a different source in its own configuration. Here, we do it with these primary boot mode pins and name these config pins. So there's only one boot mode setting for eMMC SD card, for example. But we have two eMMC SD card ports, and that decision is made by this configuration bit inside the register setting or at the sampling of the pins. So here's an example you would see there. This is not too earth-shattering, right? We have two ports, so you get a decision between one or the other. But this is how you would choose which port. So if you don't configure your boot mode pins properly for the right port that you've got your SD card connected on, you're not going to boot, right? So this is something that's caused people moving from other devices over to 64X a little bit of trouble because they were used to eMMC SD always being its own setting, and here we're using these other configuration bits just a little differently. So if it's brand new to you, probably makes perfect sense. So if you don't have any history with us, sorry for the little segue there, but like I said, it has caused some people some trouble. And another example of that, of course, is whether you're doing file system, FATFS based mode, or you're doing ROM mode for your early boot, for your boot partition. So that's another configuration setting that you would need to pay attention to. And then on eMMC, you see that they're all reserved because on eMMC, we only support boot on, I believe it's port 0 and 8-bit mode. All right, so there are no configurations that need to be done. All right, so we've got a question on how the pins map into switch values. I actually have a picture of that when we get closer to the demo. So hold on to that if you would, please. And when I get to that point, if I don't nail it, then make sure and come back to me. All right. And then we also got a question on the benefits or the trade-offs of running the bootloader in different cores. I would say it's more about how this chip was designed. I think there are probably pros and cons with a variety of ways you could have done things to achieve the level of security and safety that we wanted to have for these systems. This is the way we chose to do it by using the R5 and the DMSC together to do the boot function and then pass things over off to the A53. I'm sure there's a variety of ways you could have done it. I don't know of a whole lot of positives and negatives to that. And then we got another question on who actually loads the DMSC's firmware and the R5F's SBL. So that was in our previous diagram. Let me go back to that just real quick to make sure it's clear. So we're talking about who loads these images, and both of these are actually loaded by the R5. So the R5 copies them from the peripheral or the memory for boot to internal memory. For DMSC, recall that it is going to do a check on that image while it's in internal memory to validate the image before it consumes it by sucking it into its own internal memory. So the R5 does the basic image copy of both of these, but the DMSC is involved in making sure with both of them that they're valid images. All right, so they're kind of working together. The DMSC is making sure they're valid images, and the R5F is actually doing the copying and making that available so that they can be consumed by those cores. So hopefully that gets that question. Here's a quick slide on image formats. I'm not going to go through this too much. but you can clearly see that we've got a number of binary images that are floating around. How do we keep all that organized? How does the bootloader know where those are and you know how to work? And the only point that we're really trying to make here is that we switched over from proprietary type formats to using a standard X509 certificate to manage all of this. And then we use extensions that are standard to the X509 spec to contain the different things that we need to do our boot process. And all of that's, again, documented in that chapter 4 about from the TRM. And it talks in detail about what this is and such. Most of the time, you don't need to worry about this. Our make and build system will build this for you out of the box. So this is not something where you have to go necessarily figure this out. But if you just love to know the details, they are documented. And of course, you can also dig into our make system to figure out how we're actually going and generating these images and what we're doing to create the certificates. All right, I'm going to keep going a little further here, and I see a few questions popping up. We'll come and catch up on those here in just a second. So DMSC, I promised a little bit more detail on it. So here is your detail, specifically talking to about the system firmware that is running during the runtime of the device. So this is a dedicated core that is always running this firmware, and it is providing a number of services to the rest of the system so that there's one housekeeper, there's one management device that keeps everybody else on the same page, right? So you can't have Linux saying, hey, I want this clock set to this speed, and R5F saying, no, I want that clock set to that speed. DMSC is going to decide who wins that battle so that you know that you always get things set up properly and that DMSC always gets the final say so that you don't get a rogue R5F firmware running out there that goes off and screws up the rest of the system, theoretically. All right, so a lot of detail here on the different things that it provides. You've got your base configuration, your power management initialization for how the device is going to handle power downs. We've got your resource management, security initialization, and then there's even a one-time board configuration that gets loaded up at boot time that kind of sets up an initial configuration of the device. And of course, TI provides one of those with the SDK, but you can go tweak that to, again, specifically deal with the different configurations of your system. And that's done by how you build the system firmware and, of course, sign that so that it's valid and get that loaded into the DMSC to execute it during runtime of your system. All right, the R5 bootloader, like I said, is either an SBL in a generic or a RTOS use case or SPL in a U-boot use case. And it has a number of things that it's going to do to set up the rest of the system. It's executing from internal on-chip memory that we have. All right, we also use a little bit of the local memory to the R5F. That's called the ATCM. All right, so this sets up the MCU subsystem, gets some different things going for debug if you want to have logging, and starts to configure different pieces of the system to enable that next phase of boot, right? So if you're going out to the SD card or you want to choose something different, you can go start to configure that to do it differently. Okay. So that's the R5 bootloader. So that's those first two images that we executed and some examples about what they're doing. Really, one is a runtime system firmware that is always there providing services, and then the R5 bootloader is more a traditional bootloader that's going to run, get to the next stage of boot, and then get out of the way. All right, so I did see some questions pop up, so let's go try to answer these as best we can. The switches one I'll come back to, and then we also had one on the GPEVM switches. So I've got an SK example. Oh, I'm sorry, I'm reading Hong's answer. So I'm sorry about that. So Hong provided an answer, but I've also got a picture of that as well that we'll look at that and how the switches on the boards correlate to the boot mode settings, and I think that'll really help nail that question. And then we've got one on what is the purpose of the no boot mode that is available. And what the reason for that is because if you don't have a no boot mode, that it's always going to want to try to go run the next stage of bootloader. And that can cause communication issues with CCS or any other IDE when you're in a debug environment. So what no boot does is it allows you to say, hey, just hang out there and wait until I tell you what to do next. And you do that usually with CCS and gel scripts. So it provides a nice consistent way for a JTAG connection via CCS in order to connect to those R5 cores to do development on those and also to do bootloader testing and configuration. All right. So I've had a couple people ask about unmuting microphones. I'm sorry, we record the session, and due to audio issues and different things, we don't unmute the participant lines. So I apologize for that. That's just to preserve the integrity of the video, but we're happy to try to answer your questions if you'll put them in either the Q&A or the chat via text, and we'll try to answer them. And if you're not happy with that, just let us know, and we'll try to come back to it. All right. Okay, let's continue to move on. We've got a few minutes left here. Want to get into the Linux boot flow next, actually show you how we get from that basic initial stage, how does Linux actually come up. So a few new terminologies that we need to deal with just to make sure that everybody understands this. Modern day Cortex-A cores use ARM trusted firmware to configure the Cortex-A cores. Kind of makes as a secure monitor. In a way, this is kind of DMSC for the Cortex-A's, if you will. A little bit of a stretch there maybe, but if you're familiar with those, that might be a good analogy for you. So this is just a firmware that we need to get loaded to get the Cortex-A's configured in the proper mode. Opt is the open way to deal with security. We're always loading Opt even on non-secure devices, so that's why you see Opt in the boot flow. And then you get finally to our A53s. We run an A53 SPL, a secondary program loader. So in a proper Linux boot, the standard flow that we provide out of the box, you're going to run obviously the DMSC ROM, the R5F ROM. It's going to load an R5 SPL. All right. And if you're not in the details of Linux, of Cortex cores, R5F is actually a 32-bit core, and A53 is a 64-bit core. So we're gonna deal with that first R5F SPL as a 32-bit binary, and then we're going to load a 64-bit A53 SPL as the next binary, and then finally, of course, we get our U-boot image, which contains our U-boot prompt and our U-boot environments for doing all the wonderful things U-boot can do. All right, and that will be running on the Cortex A53s. Okay, so just a few new terms there to make sure that we're all covered so we can get into the Linux boot flow. All right, so just to let you get familiar with the diagram, so we need to have a valid power signal and generate a valid power on reset. So we got some hardware involved, of course, as we talked about. We've got our DMSC, which is going to have our secure ROM and our system firmware, our main R5, which has got our public ROM and our R5 SPL in a Linux case. And then, of course, we've got the next flavor of images, our system firmware and our R5 SPL, which are built by our make system to be included in one binary called tiboot3.bin. All right. So let's just go through this somewhat quickly because we covered a lot of the early stuff, right? So we know we need a valid power on reset signal. All right, so get a valid power source. We don't have real complex power signaling or sequencing on this device, but there are some requirements. After that, you get valid power. You do the power on reset to tell the device, okay, it's time to get going. And then we're going to start running the DMSC ROM, which is going to release the public ROM. All right, so all of that we covered in the previous diagram. So hopefully that looks familiar, even though it's visually presented in a different way. Our public ROM now is going to get the system firmware and the R5 SPLs loaded. And we're going to do that, of course, from the boot media. And down here at the bottom, we're getting our nice reminder that we're selecting the boot media and different configuration options via the boot mode pins as detailed in the TRN. Okay, so we get our SPL, we get our system firmware copied in, validated, loaded up, ready to go. And then system firmware is going to allow the rest of the system to continue to boot by getting the next stage of boot. Okay, so system firmware is up and running. R5 SPL has done his thing. We need to get the next stage of boot. All right, so we're going to go from 1 through 7, which most of those you are familiar with, now to the rest of the boot process, and now starting to talk about some new binary images that are going to get brought into the mix to finish booting Linux. All right, so step 8, the next step, is going to be our R5 SPL running. A little bit more detail about what it's doing. It's going to get DDR set up if you have a DDR enabled system, which if you're running Linux, you do. And it's going to start loading the next images that, as we discussed, is going to be our ATF and OPTI, and eventually our A53 SPL. And you can see where those are coming from over here in our boot media. So we have a TISPL.bin that has our ATF, our OPTI, and our A53 SPL. We've got a U-boot image, which has got our U-boot binary and device tree files for board configuration. And of course, eventually we get to kernel, which can be in a variety of formats. We use a non-compressed image by default, but Z image is possible as well. We just found that decompressing an image didn't have any benefits for us, so we just went to an uncompressed image. And of course, a device tree binary as well for the board configuration for kernel. Okay, so let's see how those images are going to get brought into the rest of this process. And then notice now that we're finishing up with our R5, and we're going to be switching over to our A53. So we're running our first SPL on the R5, and it's going to load ATF and OPTI onto the A53 to get the A53 configured and up and running. Then we're going to load the A53 SPL, and its goal in life, of course, as a bootloader is to get to uboot.image. Remember, uboot.image has got a uboot binary and a device tree blob. You get that. And then lastly, we're going to get our image and our device tree, usually from the file system. So we can we go and get that. And we've got now a Linux kernel up and running. And of course, the last step, which we don't dictate here, would be mounting a file system and running that, which you can do that from a variety of means as well once you have the Linux kernel up and running. All right, so 12-step process to Linux kernel, 13 if you want to include mounting the file system. But we didn't want to have 13 steps because that sounds unlucky, so we didn't do that. All right, I think we've got questions. So let's go back to, got several questions on the chat that I see. I've got one on power off. I can't really comment to power off. Hong, do you have any comments on power off?
I don't see the chat, by the way. Is it to go the?
Yeah, you got to pull up the chat window separately. It's a little, looks like a conversation icon.
So by the way, I still don't see. What's the question? One more time.
The question is just, how does power off work?
Power off. I think the basic, the generic, say reset or power saving. If you run from either U-boot or Linux, you can still the same kind of command line. I mean, kind of the command you can trigger to reset. I mean, kind of. I don't know if that's the question or not.
Okay. Yeah, I mean, power off is a pretty lengthy process. It's almost the opposite of boot. You could almost have a separate presentation of it because it again is going to interact with DMSC to go shut everything down properly and ultimately talk to possibly a PMIC or something to actually remove power from the board. So it's a combination of hardware design as well as your system design, even your Linux system, and making sure that you've got your power down sequence set up correctly in Linux. So not something, unfortunately, we're prepared to talk to you in detail in this presentation, but hopefully that kind of gives you a general idea. Also got another question about how does this sequence of Linux boot vary between Satara and other TI product families. So like I said, this is our new 64-bit family, and it by far is different. So our 64-bit family across TI processors is going to be similar. It's going to have similar concepts. We are continuing to modify and enhance the architecture with different things to meet the needs of different applications. So it does vary a little bit. So you always want to check the initialization chapter of the TRM of the device you're actually using. And this process for the 64-bit architectures is pretty dramatically different than our previous devices. So if you've worked with an AM3, an AM4, an AM57 device, yes, it's going to be quite different because those didn't necessarily have this dedicated DMSC or HSM type architecture for security and other functions like that. So hopefully that gets you some detail there. Comment that system firmware is loaded by DMSC ROM. Just to reiterate this, again, system firmware is loaded by the R5F into on-chip memory, and then DMSC goes and validates that binary image in memory, and if it's valid, it consumes that into on-chip or on-core memory, if you will, local memory, in order to continue to execute system firmware by the DMSC. So it's a little bit of a dance between R5 and DMSC. Okay. Oh, sorry. The next comment was that they got that answer. Sorry about that. I should have read all the comments first. All right. Could you in parallel start A53 and R5? To an extent, yes. There are some things that need to be done serially, like DDR config. So that is the reason why we have this boot flow. If you wanted to try to optimize things, yes, you could, as long as you're not stomping on each other. Theoretically, yes, you could start multiple aspects of the system in parallel, given the prerequisites for that were met. We provide a generic boot flow that is somewhat serial, but remember this is happening pretty quickly. So depending again on the demands of your system, it may not meet your needs. You could certainly optimize beyond that, but that's going to be a little bit of an exercise for you to do. All right, so what is the boot time from power on to U-boot? I don't remember those numbers off the top of my head. Hong, do you remember at least a ballpark figure of what our boot time is from power on to U-boot?
I don't know the exact number, but I do think we have some number. And if I can, yeah, I don't have that for now.
Okay, yeah. Sorry about that. That would have been good to include, but as you can see, we're short on time already, and we had quite a bit of content. We are looking to publish those numbers. They are highly configurable and dependent on how you can set up and do the system, as we just discussed as a previous answer. You can certainly optimize it quite a bit if you want to take on that work. But it does take time to move through the boot process and do different things. We're in the I want to say probably hundreds of milliseconds. I don't know about U-boot. U-boot has a pretty big environment, and getting that loaded and reading the device tree and some of that stuff does take time. And we don't optimize any of our device trees to make it easy for people to consume. So there's quite a bit of opportunity there to shrink some of those images that can speed that effort up quite a bit. So our out-of-the-box numbers are not going to be, certainly what you could achieve if you did some optimization. And there's one about boot image validation. I'm going to let you handle that one if you could in chat. And I'm going to go ahead and move on so we can hit the last of the material because it's got one detail that I promised to show. So we provide
Okay.
two EVMs at this point that you could use as examples for how these systems boot up. We have an evaluation module and a starter kit. We have links to both of those in a slide at the end of the presentation. So I'm going to show just quickly each one of those. This is the EVM slide. So this is a green board if you have one of these. Both of these boards have a similar two bank row of switches that can be used to modify those 16 boot mode pins. So here you're actually seeing a picture of the board and its different switches, and you can see that this is 0 through 7 and 8 through 15. And you put one in the on position for a 1 or off, obviously, for a 0, and some of the different modes that are supported. Here's the picture that I was hoping would make things a bit more clear. This is on the starter kit. So this is a smaller whiteboard that is newer. So if you have one of these, this is a $99 board that you can purchase that has an AM64x on it. And it has the same switches. Unfortunately, the silk screen is a little messed up. So you have to be careful when you're reading through these, which one is which. The on position is up toward the on of the switch. All right, and off is opposite that, obviously. And then here is the picture diagram that I was hoping would help kind of explain. You've got your switch 3, right, which is this one, represents your upper bits, or no, pardon me, your lower bits. Sorry, bit 0 clearly indicated over here. And these are clearly mapped out to each one. If you remember, if you have that good of a memory, our PLL configuration is our first 3 bits, our primary boot mode, our primary boot configuration, and then we get into the backup stuff that fills up the rest of the bits. All right, and then here is a picture of SD card boot on this board, which comes directly from our quick start guide. So the first thing you typically do with these boards is you go burn an SD card. We provide a variety of ways to do that in a cross-platform nature. Once you have an SD card with Linux on it, with all these cool images that you've learned more about today, you can put that in the board and then configure these boot mode pins in this way for the SK at least. And you should boot directly off of the SD card all the way to the Linux boot prompt, which if you want to, you can log in with root, which is our password for all of our file systems, and that will get you into Linux on our Arago distribution, which provided with all of our SDKs. All right, a couple of quick links here. So the quick start guides that I mentioned, we include links here. I will post a PDF of these slides as well on the same E2E post where hopefully you found this, and you can get to that. It will also be they're also posted along with the video. And you can get to these links, but you can also just Google these things and you should be able to find them pretty easily. These quick start guides are wonderful little short documents that just get you very quickly up and running with Linux on either the EVM or the SK, from burning the SD card to booting them to playing around a little bit with some of the things that are included on there. Okay. And then once you get to that, you can log into root. You can start doing a variety of wonderful Linuxy type things. All right. I'm just going to try to, we got just a minute or two here. Let me try to hit some of these questions. We got one question. Is it possible to use Ethernet boot to load U-boot only in order to flash images on eMMC or OSPI for the next boots? Absolutely. That's how it's designed. You'll even find primary and backup methods where you can have a primary boot off of an eMMC, for example. If it's empty, obviously you're going to default off of that, and you're going to go back to your secondary, which in this case could be Ethernet. Our Ethernet support is not there yet in the current SDKs, just to save you some trouble of going and trying this. We do plan to add that toward the end of the year, but you can do UART for now in much the same fashion. So you can use UART to load U-boot, and then you can use U-boot to flash your devices. And then once you're to U-boot, you can use Ethernet. Ethernet is included in U-boot. It's just not a, we don't have the boot configuration added yet. So that is coming, and that's exactly how that's intended to be done. So use UART for now, and since you're only copying over U-boot, it's really not that bad. but Ethernet, of course, would be faster and allow you to program a whole bunch of boards in less time. And we're going to take this as our last question because I noticed that it says it's 11 o'clock and I want to respect your time. But how do you load the PRU cores? And that's a great question. And this is actually a generic answer to the other R5 cores as well as the M4 core. So any of the other cores on the device. By default, with our Linux SDK, we're going to load those in Linux. So we're going to use remote proc to load up your PRU cores, specifically your R5 cores. And then I believe M4 support has either been added in the most recent SDK or it will be added very soon. So all of those cores can be added through Linux by putting a firmware blob into your file system and using remote proc to load those either at boot time or at load time. So generally the natural thing that follows after that from the great engineering minds I'm sure we have on the call is, but how do you do it faster? And that's where you would have to start modifying that secondary bootloader or start doing something in U-boot in your secondary program loader, which we don't have any of those things enabled quite yet. So the standard way to do it today is through Linux. And yes, that does mean that Linux has to come up before those cores can be added. We understand that people want to do that earlier, so we are looking at adding support for that. Before we add support for it, that's something that the user would have to do themselves. All right. So thank you very much for attending. Here is a quick list of some of the links that we had, including the boards and our documentation for SDK, where to get the SDK. So hopefully those are useful to you. Like I said, those will be in the PDF file as well. And we just wanted to stop and thank you so much for spending time with us today. I hope that this was useful to you. I want to thank Hong as well for helping me moderate this. Had really good questions and it was difficult to keep up with all of them. So thank you, Hong, for helping me with that. And again, everyone, thank you so much. I hope that was valuable for you. Hope you'll come back and join us for a future Satara webinar via the E2E links. That's our engineer to engineer forum that you can find easily by Googling. If you have ideas for other webinars, we'd love to hear your feedback and certainly want to provide content that is useful to you as you use Satara devices to solve your embedded systems needs. So thank you once again for everyone, and I hope the rest of your day is awesome. Thanks much.